Happy to present our speaker today, Austyn Matheson. Did I pronounce her last name right?
Yes.
Okay. She's a PhD student here. She's working with Dr. Tannen Schmidt, who some of you might know was a PI here, but he's now in Connecticut, I think it is.
Yeah.
And Michael Scott. So, as usual, I want to say a couple quick words to introduce Austyn, and then I'll let her get on with her talk, which is titled RHPRG4 Optimized Collagen-Based Scaffolds for Cartilage Repair. So, as you may have guessed, Austyn has a strong background in engineering and bioengineering specifically. So her bachelor's degree was in Queen's University in Ontario, where she studied mechanical engineering with an option for a specialization in kind of like bioengineering stuff. For her master's, she went to Trinity College in Dublin, where she received a degree again in bioengineering. After this, she took a little bit of a break from academia, and she went on to industry, where she spent 2 years working as the lead production engineer for a company in Toronto that was developing point-of-care diagnostic devices for patients. After this point, of course, I guess she saw the light and decided to come back and get her PhD. And that's when she joined us here in Calgary, working on this project with Drs. Tannen Schmidt and Michael Scott. Specifically, her PhD work is looking at proteoglycan 4 in equine joint disease. Austyn plans to wrap up her research this year, so I invited her over to talk about, some of her results so far, as well as a little bit about her plans, some of the experiments that she's still running. She says she's going to talk about today as well. So that's kind of professionally all I wanted to say. Of course, we always like to end with a few fun facts about our speakers, what they do outside of work. So Austyn actually has a lot to talk about here, which is awesome. So in high school, she took a class of float. And so I guess that was classes, but you were on a boat and sailing.
Yeah.
And during that time, you went from San Juan, Puerto Rico, all the way to Victoria, BC. She's also, as many of our speakers are, passionate about sport and physical activity. She did her yoga teacher training in Costa Rica before she started her PhD. She's an avid runner and enjoys running home from work, to and from work. And I think we can all appreciate the desire to run from work. And finally, she enjoys biking and has actually taken part in 2 bigger tours. So she did a 19K from Hartford en route to New York, and she did another one for 200 miles from Maine all the way to Rhode Island. So with those out of the way, I think you know a little bit more about you now. I'm going to pass it off for your talk. Thank you very much for coming.
All right, thank you very much for the introduction. So this talk is going to be on the second half of my PhD research, and it's on a collaboration we did with the Royal College of Surgeons in Ireland. And yes, so it's on a PRG4 optimized collagen-based scaffolds for cartilage repair. So how do I click there? Okay. So the presentation structure will follow that. I'll give a bit of a brief introduction, and then the 3 results sections, first being biomechanics, so looking at the lubricating ability of collagen-based cartilage scaffolds, and then the structure of scaffolds when PRG4 is integrated into the bulk material, and then the cellular response of mesenchymal stem cells with the PRG4 optimized collagen-based scaffolds, and then a quick summary. So to start, just a quick section on about me. So I think I have to give a good introduction, but I'm actually born and raised in Calgary, and then I did my mechanical engineering degree at Queen's. I came back and I worked for an oil and gas company before going off to pursue my master's at Trinity College. And then at Trinity College, I worked for the Royal College of Surgeons, and we developed a collagen-based scaffold for peripheral nerve repair. So this is where this collaboration kind of came into play, because I contacted them again for this project. After which I moved to Toronto, and so this is the golden cartridge, which is a point-of-care molecular diagnostic device. And so we gave this as a joke to our boss. And then since then, I've been in Calgary since May 2016. And recently, I actually went to Connecticut, where Tannen Schmidt has since located at the University of Connecticut Health Campus. So I lived in Hartford, Connecticut, which is full of beautiful buildings. And this is my favorite building in the capital. And then I just spent 4 months in Dublin, Ireland. So if anyone knows a good place for Guinness, let me know. I have a fondness for it now. So let's get in. So as I'm sure you're all familiar with, being here in the Human Performance Lab, you know the synovial joint anatomy. So the two points of interest in this talk will specifically be on synovial fluid and these two molecules within it, proteoglycan-4 and hyaluronan. And these two molecules are very important to the lubricating ability of articular cartilage. And then also within cartilage are all these components, but again, specifically, I'm interested in proteoglycan-4. So why is that important? Well, that's important because in the case of osteoarthritis, we have eroded cartilage and malfunctioning synovial fluid. So there's a poorly lubricated joint, lots of stiffness, and this evidently needs some form of treatment. So that brings us to tissue-engineered osteochondral scaffolds. So this is what I've been working on with the Royal College of Surgeons in Ireland. So what happens with the tissue-engineered conduit is materials are either natural or they're synthetic-based. And so what they do is they implant this biomaterial from the bone up to the cartilage surface. And the concept is that the mesenchymal stem cells influx into the biomaterial that contains the appropriate biological, mechanical, and other cues that induce osteogenesis in the bone layer and chondrogenesis in the cartilage layer. So these biomaterials can fully heal osteochondral defects. So this is the biomaterial developed by the Royal College of Surgeons in Ireland, and this is a highly porous collagen-based biomaterial. So they're fabricated by a freeze-drying technique. So it's an iterative process that creates this 3-layer construct for osteochondral repair that produces these highly interconnected pores. This is a scanning electron image, and so cells can infiltrate within the scaffold, and which effectively behaves like a home, so that cells can become either bone cells or cartilage cells. And then the collagen material actually possesses a lot of, I know it's hard to see, but sites for cell attachment. So cells can attach and grow within these new homes and become new tissue. And these materials are optimized, their mechanical properties, their compressive stiffness is optimized for the appropriate cues for chondrogenesis and osteogenesis. So why is this important? So this led me to think, I've been studying PRG4 lubrication on a cartilage-to-cartilage interface. My question is, what is the lubricating ability of these collagen-based biomaterials? And this is somewhat unknown. So we know that the bone layer is composed of this collagen-1 hydroxyapatite, and then it is composed of collagen 1, 2, and hydroxyapatite. This is for calcified cartilage regeneration. And then the surface layer is composed of collagen 1, 2, and hyaluronan. And so each of these layers has been optimized for the regeneration of each layer. But when we consider the cartilage layer, it actually has 3 zones, a deep, middle, and superficial zone. And one protein in particular, the one I've been studying, PRG4, is present at the uppermost surface, and it's very critical to the lubricating ability of cartilage tissue. So this gave me 2 questions. One, do these collagen-based biomaterials support lubrication? And 2, would the addition of PRG4 onto these scaffolds enhance the lubricating ability? So just quickly, proteoglycan-4 is a large mucin-like glycoprotein that has 3 functional domains. Its N-terminus forms dimers between PRG4 molecules. Its mucin domain is extensively glycosylated, meaning it holds on to lots of water, and this is important to its lubricating ability. And its C-terminus actually anchors the molecule to cartilage surface, and that configuration imparts is important to its ability to lubricate. So we know that PRG4 is present at the uppermost surface of cartilage, and it's present within synovial fluid. So it functions to lubricate, it prevents cell protein adhesion, and it's anti-inflammatory. So proteoglycan is a really important protein for cartilage and cartilage lubrication. So introducing it to a collagen-based biomaterial could be potentially advantageous. So we went and created a PRG4, a recombinant human PRG4 optimized collagen-based scaffold for the purpose of cartilage repair. So the beginning of the project, we wanted to establish a foundation. So what are the biomechanics of these collagen-based scaffolds? So I developed an in vitro friction test to assess the lubricating ability of these scaffolds. And then we also investigated if PRG4 attached to the collagen-based biomaterial. The second part, we integrated the protein into the bulk material with the method that they used to produce the collagen-based scaffolds. So we integrated the protein, and then we characterized the structure and then its lubricating ability. And then finally, we looked at implementing this in an in vitro test. So we looked at the effect on porcine MSCs. So we characterized the cell proliferation and the chondrogenesis, because this was the cartilage layer only. So then to start, just for the foundation, I'm going to just briefly discuss cartilage lubricating modes, because this influenced how we designed the in vitro lubrication test. So let me just get into this. So the lubricating modes, the lubricating ability of a material can be quantified by the coefficient of friction. And so that's the force of friction divided by the normal force. So this is shown by this can be illustrated by the Strybeck curve. So this is adapted from a mechanical component system. But for the purpose of cartilage, at the onset of motion, there's hydrodynamic lubrication. So that's when there's a fluid film separation, and hyaluronic acid, which is very viscous. It provides a lot of viscosity to synovial fluid. It's important in providing the low friction observed here. And so as cartilage depressurizes, the layers begin to come into contact. So there's a mix between solid contact and fluid contact, and it transitions into this elasto-viscous lubricating mode. And then finally, as the fluids in the cartilage is completely depressurized, cartilage becomes directly into contact, and proteoglycan 4 is really important to lubrication here. So both of these molecules present in synovial fluid, proteoglycan 4 and hyaluronic acid, impart significant lubricating ability to the cartilage surface. And here, this kind of depicts how proteoglycan 4, it's also known as lubricant, is anchored to the cartilage surface, and it retains hyaluronic acid close to the surface as well. So this is critical to its ability to lubricate. So collagen-based scaffolds are actually porous open cell foams. So if you can kind of see that, you saw that scanning electron image of them. So when they're being strained, there's a linear elastic region from the 0 to 10% strain, and then the struts begin to buckle and collapse. So there starts to be a collapsed plateau, and then a final densification at 80% strain. And so why is that important? Well, that's important when you consider its potential ability to lubricate. So if the pores are open and fluid can outflux, there might be more of a hydrodynamic lubricating mode occurring. But then as the pores collapse and close, it's potentially transitioning more into a boundary lubricating mode. So both of these synovial fluid constituents in the boundary lubricating mode likely have important roles in supporting a collagen-based scaffold when it's implanted inside a body. So how did we assess the friction test? We used this is taken from a cartilage to cartilage friction test. So we adapted our test from this idea of a stationary contact where the two surfaces come into contact, they're depressurized, and then one surface is rotated against the other, and then you measure the torque the torque and the resistance to motion, and that is used to quantify the coefficient of friction. So for this foundation, for this first part of the project, we developed an in vitro friction test, and specifically to look at the lubricating ability of these collagen-based scaffolds, and the role of the compressive strain, and the role of synovial fluid lubricants. And then we characterized PRG4 adherence to the scaffolds. So this is the configuration we used. I don't know if any of you have used the Biomomentum Mach 1, but that's the machine I used for this test. We placed a hydrated scaffold between a sandpaper surface to hold the base in place, and then it was articulated against a glass slide. So the scaffold, how the test began is the surface comes into contact and it applies a strain, and then there's a rotation in 360 degrees in both directions. And we tested the scaffold in 4 lubricants, one being PBS, which is our negative control, and then hyaluronic acid solution at a physiological concentration, and then PRG4 also at a physiological concentration. These were the test solutions. And then we examined as well bovine synovial fluid as the positive control. So we calculated the coefficient of friction by the torque divided by the normal force at equilibrium after a stress relaxation times the radius. So I completed that at a stress relaxation of 10%, 20%, 30%, 40%, and 50%. And then we calculated the coefficient of friction here. So our first finding was that synovial fluid lubricants did not alter the equilibrium force reached after stress relaxation. So this is an important finding because that value is used to calculate the coefficient of friction. So any change in the coefficient of friction would result from a change in the resistance to motion. So going into that, we found that synovial fluid lubricants enhanced the lubricating ability. So both PRG4 solution and bovine synovial fluid solution, or normal bovine synovial fluid, enhanced the lubricating ability significantly across each of those compressive strains during the stress relaxation that was reached. So this is a really interesting finding, and hyaluronic acid solution did not have an effect. So compared to normal cartilage on cartilage tests, we would see typically a coefficient of friction of synovial fluid being 0.02 or much lower, and then a PBS being about 0.2 to 0.4. So our test was within this range of a cartilage on cartilage friction test. So just for comparison here. So lastly, we looked to see if PRG4 bound to the collagen-based scaffolds. So we soaked the collagen-based scaffolds in PBS, PRG4 solution, or synovial fluid overnight at 4 degrees, and then we rinsed them again overnight at 4 degrees, and we found that PRG4 from both the solution and from synovial fluid adhered to the collagen-based scaffolds. And so that's compared to a bovine cartilage sample, just to show that we were able to actually, this is indeed what's happening to bovine cartilage as well. So this is an interesting finding because perhaps PRG4 is binding to the collagen-based scaffolds in a way that it does to cartilage, and it might be important to its ability to lubricate. So in conclusion, we developed an in vitro friction test. We found that PRG4 solution enhanced the lubricating ability of scaffolds and that adhered to collagen scaffolds. So ongoing here is that we want to assess the lubricating modes. So to do that, I need to complete additional testing to examine the effect of stress relaxation duration, and then also the changing sliding velocity. So these are ongoing to go. So next, we completed the integration. So we integrated PRG4 into the bulk material properties of the collagen scaffolds. So we characterized the porosity and the pore size, the lubricating ability of the scaffolds, and the compressive stiffness of the scaffolds. Slide. All right, so for all these scaffolds, the materials that were used were collagen 1 at a 0.5% weight volume, and then hyaluronan at a 0.05% weight volume. And so how they're made is the materials are dissolved in 0.5 molar acetic acid, and then they're blended thoroughly. So blended until you can't see any kind of chunks or components left. And the lyophilization cycle finishes at a minus 40 degrees temperature, and that's really important because that dictates the pore size. So if you have a very low temperature, like it should be minus 40, not positive 40 because they're frozen. But higher temperature, so minus 20, would produce higher pore sizes, and a very low temperature, say if you were to freeze it in liquid nitrogen, would produce very tiny pore sizes. And if they're very tiny, then the cells can't infiltrate. So this is optimized for MSC integration, specifically for chondrogenesis. So we incorporated PRG4 into the scaffolds at low and medium and high concentrations. And first we checked to see after a 24-hour incubation of scaffolds in PBS, we examined by Western blot to see if PRG4 was intact. So this process didn't damage the protein, which was a good finding. And then we also have relative estimates of how much is released over the course of 24 hours. So because the low concentration is so low, we weren't able to detect it on the Western blot, but for the other two, we have about 80% released within 24 hours from the medium scaffold and about 16% released for the high scaffold. So these are interesting findings. And then we examined the pore architecture. So this is a JB4 embedding and then staining by toluidine blue. And so these sections kind of can display the pore structure. So for the collagen control, we would expect this homogeneous distribution of pores that are roughly the same size. But what was interesting is that for the high and also the medium and low images not shown here, but the pores are much larger. And so not entirely sure why this occurred, but this is important because this may affect chondrogenesis or any cellular activity. So we saw there was a change in the pore architecture, although they were highly interconnected and distributed pores. So interesting here. Next, we characterized the lubricating ability of the PRG4 incorporated scaffolds, and we found that adding PRG4 to these scaffolds significantly improved their lubricating ability, which was a great effect. But the one negative side to this is that it also decreased the compressive stiffness significantly. So the findings here were that we were able to produce scaffolds with high porosity and intact PRG4. It enhanced the lubricating ability, but it decreased the compressive stiffness. So ongoing is we're characterizing the PRG4 release timeline with ELISAs and more quantitative methods. And then we're going to produce, or we have produced, a collagen hyaluronic acid scaffold with a superficial film layer. So this will ideally maintain that enhanced lubricating effect, but then address that issue of reduced compressive stiffness. So what that looks like, this dual layer, is they're produced by, you place this collagen slurry in these molds, and they're put under a fume hood, and they're slowly dehydrated over the course of about 3 days until all the liquid's removed. And then it forms these very thin films that are about 20 microns thick. And then they're rehydrated, and we add a collagen slurry on top, and then they're refreeze dried to make a bilayered scaffold. And that looks like this by a scanning electron microscope. So it has that film layer on top and then that porous scaffold beneath. So the concept here is that when we do this with PRG4, it'll have enhanced lubricating ability on the surface, but a porous and a better compressive stiffness properties below. And then, this is another image of what that scaffold would look like. Maybe hard to see, but the film is there like this. So lastly, to go into the implementation. So I had a few questions before examining what the effect of PRG4 when it's integrated into the bulk material properties, and these were driven by what we know about PRG4. So we know PRG4 enhances cartilage lubrication, and we also know that treatment of PRG4 through intra-articular injection, and then this is a very common model for inducing OA in rodents, the acute cruciate ligament transection. And if you inject PRG4, it will preserve the cartilage volume and thickness. It will preserve gait and biomechanics, and it can preserve lubrication. So it's also been used as a gene therapy, and it has anti-inflammatory effects. So a potential negative side effect of introducing PRG4 is that it's anti-adhesion. It is anti-adhesion, so it prevents cells and proteins to bind, and actually soaking cartilage explants in synovial fluid prevented their repair. So this could have been a negative finding if adding PRG4 to these scaffolds prevents cells from attaching and integrating. So this is a potential thing we wanted to examine. And then we had a final question is, could PRG4 MSC mesenchymal stem cell differentiation to be superficial zone chondrocytes? And this was thought for two reasons, or for one reason is that when MSCs are co-cultured with superficial zone chondrocytes, they become more like superficial zone chondrocytes. And that looks like superficial zone chondrocytes specifically produce PRG4. So one reason, and it was suggested in this paper here, is that those cells, the superficial zone chondrocytes, are secreting PRG4 into the media as they're growing, and that might have an effect on guiding the differentiation of the MSCs to superficial zone chondrocyte-like fate. And that's important because with a cartilage implant, you want that top layer to be hyaline-like, producing, PRG4 supporting lubrication. So these were kind of the things we were wondering about when we designed the cell study, or the cell studies. So the first cell study we did was we examined, it was just a 7-day study to see if the PRG4 integrated scaffolds affected MSC adhesion and proliferation. And the second one was to examine the effect on chondrogenesis. And then this last one, again, is examining the effect of PRG4 on chondrogenesis, and this is ongoing. So how did we do this? So we pre-hydrated the scaffolds in media, and we seeded 400,000 cells per scaffold, so that was evenly on each side, and we cultured them in, for 7 days. So the groups we studied were the collagen control, PRG4 low, medium, and high, and then these are grown simply in expansion media. So what we found here, so this first result on the left is the metabolic activity. There was an increase in metabolic activity from day 1 to day 7, and there was a significance between the control and the PRG4 high group in metabolic activity. But overall, this would suggest that cells are growing, they're attaching to the scaffolds, and they're not being prevented from binding, which was somewhat of our fear from the anti-adhesive effect of PRG4. And then in addition, the DNA wasn't significantly affected by the groups. So although we saw this kind of drop off, this is potentially, expected with the cells as the activity decreases and the cells kind of die. Some of them will die after the initial seeding period. So, but it was good because we didn't see a significant difference between our PRG4 optimized scaffolds and the control. So then the second study we did was, again, doing the same pre-hydration and seeding of cells. But for this one, we completed this over the course of 28 days. And we excluded the low group just to make the numbers fewer and easier to control. And we grew them all in chondrogenic media. So all these components are added to, and specifically TGF-beta is a very important chondrogenic factor for inducing MSC differentiation. So this was the kind of the cell study we did. So looking at our first result, the H&E stain, so I included just a quick picture here on the left. So this is what it should look like. So that's the control cartilage is pink with the dark purple stains are cells. And then when they're decellularized, you see the gaps there. So for our control medium and high scaffolds, we saw a nice dispersion of cells within the scaffolds at day 14. But something that we noticed that was somewhat negative is that there seems to be less cells at day 28. So this was just something, not entirely sure why that occurred, but we did see that there were a nice number of cells at day 14. And so that followed with our biochemical analysis. So we completed a metabolic activity assay. So over the course of day 1 to day 28, there wasn't a very significant difference in the metabolic activity. But the DNA was interesting because at day 14, we saw a higher metabolic activity for the high scaffolds compared to the control and medium scaffolds groups. But this wasn't very evident on the H&E stain. So next we looked as well at the GAG production, and that's a marker of chondrogenesis of MSCs. So this is done by Safran-O. And so this is what a Safran-O stain should look like. So pink would suggest sulfated GAG production. And then as you remove it, it's more blue. So as you can see, we didn't have chondrogenesis at all. And so this was somewhat surprising and disappointing, to be honest, because this is a 28-day cell study. But we had a few hypotheses why. So this was actually just completed a couple weeks ago. And that's why we have a cell study ongoing. But one is that the cells we used here were passage 4, so they had perhaps lost their ability to become chondrocytes. And two, the TGF-beta we used in this study, what other groups completing other tests on chondrogenesis also observed that their cells were not becoming chondrocytes. So they weren't staining red, and they weren't differentiating and showing GAG production. So that's also shown in this GAG assay. So this is a very low concentration of GAG produced based on the number of cells seated on these scaffolds. So this isn't what we would have expected, especially in the control group. So it shows to us that there's not really an effect compared on the medium and high compared to the control, but it's somewhat inconclusive. So the one finding that we need to complete again is that I found through immunohistochemistry that this is a PRG4 immunohistochemistry stain. So what was interesting here is that this is the high scaffold at day 28, is that the bright red that would show where PRG4 is localized, it's in somewhat of the pattern that is observed for the mesenchymal stem cell positions in the scaffolds. So need to complete DAPI staining to show that the stains coincide with PRG4, and that would maybe suggest that PRG4 is being produced more on these scaffolds. But this is an ongoing work, but this was an interesting finding we found in a few of the scaffolds. And here's a select image. So the outcomes we found were that PRG4 didn't impede the porcine MSC attachment or proliferation, but the effect so far on chondrogenesis is inconclusive. So the ongoing is to assess PRG4 release into the media, and then characterize PRG4 localization by immunohistochemistry. So our ongoing study right now is being completed by Dr. Tom Hodgkinson, and so he's looking at comparing, these are on human mesenchymal stem cells, and so doing a control group compared to a PRG4 treatment and having both expansion and chondrogenic media. So the goal will be to see, does PRG4 have an effect on, it'll be on the PCR, so gene expression, SOX9, aggrecan comp, to see if those markers are altered by treatment. And then this will be done in parallel to another scaffold study grown out to 28 days. So in summary, we optimized collagen-based scaffolds for cartilage repair with PRG4. We assessed the lubricating ability of scaffolds, and then the structure of integrating the molecule within, and then the cellular response. So that's all, and I'd like to thank all the many people that have helped with this project. And yes, do you have any questions?
Perfect. So I'll open up the floor to any questions. In that case, oh, sure, Dave, go ahead.
So where did you get the MSCs that you used?
We got them from, there had been an experiment that was completed before. So this is somewhat of a preliminary test. So these cells had been used for other chondrogenesis tests, but they were from, I believe, the bone marrow of porcine.
Yeah, that gets to my question, actually. There's a lot of MSCs floating around in synovial fluid, and it turns out that when you do lineage-specific induction, those like to become chondrocytes versus bone marrow, which like to become bone. So some of the outcomes may be influenced by the source of the cells that you're using, whether or not they're used to it. And the ones in the synovial fluid have been living in synovial fluid, which is full of PRG4 and HA, so they may be much more adaptive to that environment than the bone marrow cells, which are probably in a very different.
Yes, that would make sense.
I'll ask a question before I pass it to the audience. It has to do with your friction tests.
Yes.
And I wanted to ask, does the pressure of the fluid have any effect on its lubricating ability? And if so, does the test recreate kind of realistic pressures in the joint, or is that not something that's looked at?
So I think if you mean pressure, we normalize the load cell once the whole setup is under the lubricant. Mm-hmm. So what we found is that with the stress relaxation, there wasn't a change based on the lubricant it was in. And I would have thought that it would be different with synovial fluid. I thought it would provide a resistance to compression with the matrix. But I think these matrices are so porous that the fluid just exudes out.
Yeah.
So there really isn't an effect based on the lubricant that it's in. The same way that, I mean, the difference with being with a cartilage sample, which would resist that flow outward.
Sure. Ian?
What's the decline in resistance to compressive strain with the PRG4? Do you think that's related to the pore size?
I was thinking that I had thought after I measured the compressive stiffness and saw that it would be related to the pore size, that there's the struts are more dispersed, but they're all the same size. So if the pore size is larger, you would expect that the struts would actually be thicker. So it's hard to really say what the reason is, but that was initially what I was thinking, and I actually predicted that the pores would be larger based on that finding, but somewhat inconclusive. It's hard to say.
And could you test that just by using your different temperatures of setting everything? You said that you can get smaller pore sizes at -80 than -40 than -20. Could you just test that and see if that might explain anything?
Yes, I think, well, I'm not sure if the pore size changes the compressive stiffness that much of the scaffolds, if they were just being collagen-based, if they're simply collagen-based biomaterials. But typically they enhance compressive stiffness by cross-linking the collagen, and then that has a very strong effect on its compressive stiffness as opposed to the actual freeze-drying, the ultimate freeze-drying temperature. I don't know if that answers your question.
So you don't think that the pore size has an effect?
I think it does, but I'm not sure how to test it.
Okay.
Yeah.
Yes.
Austyn, when I was looking at the microscopic pictures of the collagen matrix, I thought that it looks more like trabecular bone than cartilage. Like cartilage extracellular matrix, or cartilage is lots of matrix with distributed lacunae, little pits here and there that the cells sit in, and so mesenchymal stem cells are going to be influenced by the mechanical environment, and if they go into this synthetic product that to me looks to my eye more like trabecular bone, maybe that makes them want to become more like bone cells. And maybe if that superficial layer of that implant for the synthetic product looked more like cartilage extracellular matrix, then that might make cells happy. Would it be possible to create that?
So we did actually, there's a result I didn't include here because they're kind of messy because we're the first to do it. We did culture cells on films, control films, medium and high. But the thing that occurs is the cells really contract and pull them in. So you see the cells actually don't infiltrate film, they just grow on the surface. And I mean, I think that's the one thing as well that you're observing with the stains is that the cells really contract the scaffolds as well. And that's because we haven't cross-linked them. Because we're concerned about the effect on PRG4. So we did cross-link PRG4 scaffolds by a DHT, which is a vacuum oven at 105 degrees. So I'm going to be looking at the molecular weight of PRG4 released from those scaffolds to see if it remains intact, even though we don't think it will, because that would keep those pores open, less contracted, less like trabecular bone. But then that's why we saw that, because we didn't cross-link these scaffolds. So they really are contracted by the cells.
If you put cells into the cartilage slurry product prior to freezing, and then put those cells through the freezing cycle, would they survive?
I think they would probably die, yeah. It's a 24-hour cycle. And it's minus 40 degrees, so.
We are using stem cells in clinical applications all the time that are coming frozen in liquid nitrogen. But they're not in a zero.
But the second part of the freeze drying process is dehydration, right? Removing all the water from there. Yeah, so maybe that would kill them, at least. Maybe not the freezing, but the
Yeah, Dave?
So you think the PRG4 is binding to the scaffold? If it's not changed, it's probably not covalent. So you think it's just an ionic interaction with some set of sites that are just sitting there with some affinity?
I know. I wish I could. I wish I could determine that, because they've looked at how PRG4 binds to cartilage, and they will make different combinations of the different parts of the PRG4 molecule to see if it binds by the C terminal or the N terminal. So we would need to maybe do something like that to see what part of the PRG4 molecule is binding to the scaffold, and that would maybe show that. But then how it's bound, I'm not entirely sure.
And you quote unquote optimized it, so you could have saturated it. Do you think that by saturating it, you could have interfered with the cellular interactions with the scaffold versus having some there, but not saturating it to interfere with cell activity?
The concentration we picked was based off the 2 microgram a mil as a kind of a guesstimate based on how nobody's really quantified the exact concentration at the cartilage surface, but how much is produced by cartilage cells, and then how much they stain for kind of in certain cross sections. So we went up magnitude and down a magnitude. So that's how we picked the concentrations to see if we were saturating it or not. But because the cells still adhered and integrated within, it didn't affect the adhesion and proliferation and growth. So I'm not sure if it is saturated yet.
Okay. Any more questions? Yeah, Tim?
Austyn, in the early work where you were testing the biomechanical and determining the frictional coefficients, I remember, at least from one of the figures, that the PRG had a lower coefficient of friction than the bovine synovial fluid. Is that right?
And, yes.
Yeah.
Yeah.
So it was actually your constructed solution was actually better than the in vivo, sort of the standard that you'd see in the bovine. But did you look at whether or not the lubricant breaks down? Like, did you ever look to see whether there's fragmentation? I'm wondering if the bovine lubricant stayed as a long chain big molecule, and the one that you had became smaller, but actually the smaller pieces actually performed better. I'm curious about what shearing would do to the molecule, because you did say they're monomers that are all attached together.
For the tests, I used fresh samples. So I would have used, so Tan & Schmidt owns the patent to PRG4, and so Lubris generously provided a lot of the protein. So for all the tests, I diluted fresh PRG4 sample, and then bovine synovial fluid, I took fresh each time. So these tests take for each lubricant about a full day. So with other characterizations we completed with the cartilage on friction test, we didn't see a breakdown over the course of, usually it would take us a week to do one kind of test, because the cartilage samples, they are a 2-hour test. And so there wasn't a loss of a lubricating ability wasn't seen from even those kind of time points. So I'm not sure if the proteins have broken down. That would be something we would need to look at to see if they are actually fragments. So to take that solution and run a Western blot to see if that was the case.
Yeah.
In your friction tests, you had a hyaluronan group and a PRG4 group, but in your introduction, you suggested that the PRG4 interacts with hyaluronan, keeping hyaluronan at the boundary layer.
Yes.
Why did you not test the interactions of hyaluronan and PRG4 in your friction tests?
I did, but I didn't have time to complete that data. So I had initially completed both that combination, but for these results, I hadn't had time to do that.
Okay.
But yes, because it's true that they interact synergistically and independently.
guess I have a question about like the integration of these scaffolds. Like, if it eventually works and it seems like the plug has this great lubricating ability, you then just like shove it into the defect and it'll attach to the cartilage on the side, right? So the next thing I thought in people with OA, they have like the composition of the synovial fluid changes so that it becomes. So how is this just a short-term solution because you fix one defect, but a defect occurs somewhere else or another, you know? Or what's the kind of like long-term idea behind this? Like if you fix one defect, will you not get another defect, or will you eventually get another defect and then you have to fill that defect with another plug?
So I'm not entirely sure of the patients that they've implanted these in and what they've looked at. But so these scaffolds have actually been implanted, I think, in 6 humans so far, and none of them have come back to the clinic for feedback. So that would suggest maybe a good outcome. But kind of the added benefit of having PRG4 is there's a few reasons. So if it's integrated onto the surface of the scaffold, 1, it's providing lubrication. 2, PRG4 has an anti-inflammatory effect. So when you're drilling a core down into the bone layer, there's going to be inflammation. So PRG4 interacts with TLR4 and 5 and CD44 and has these anti-inflammatory roles. So if it's released into the synovial fluid, then perhaps it's helping that as well. So there's those potential added benefits, but you're correct. So if the synovial fluid's poorly lubricating and then that's occurring in other locations, there could be more defects formed.
As a follow-up to that, how long have the human people with the implants?
2 years.
2 years? Okay.
Yeah.
This has also been used in a couple of studies, or at least one clinical case of a horse, and I have some experience with similar products in veterinary applications. And you know, if it's a situation where there's diffuse osteoarthritis, like many people experience in older age, or rheumatoid arthritis, or multi-joint arthritis, it's not going to be a useful application. But if there's a specific and focal trauma, there's quite a few examples of that, and you can preemptively, or you can treat early on in the process that area of focal trauma and have better joint function by repairing that specific area. You may prevent that joint from progressing, getting post-traumatic osteoarthritis. So in the horse application that is used, it's for that specific area of cartilage damage. They can create an engineered osteochondral graft that will fit into that defect and integrate into the bone better than just a chondral research graft. It has some success. In those studies, they've done recheck arthroscopies a few months later to examine the appearance of the graft, and it's level with the surrounding cartilage layers, and you can see a seam where the graft interacts with the cartilage, but it's at a reasonable level, and seems intact. They haven't sampled it. It's not hyaline cartilage. It's somewhere between fibrocartilage and hyaline cartilage. So, you know, it's a specific application for what they use.
We have time for a few more if anyone has questions. But it looks like no. So on that note, please join me in thanking Austyn again.